Well, everyone, there's another video that is tied to the ITS2300 class, and today we will talk about Ethernet. Again, just a basic introduction. As I typically do, we'll take a look at the book that we've been using in class for that, and this is the Stevens Fall book. The content we're interested in for this video is chapter 3. This is the first of many chapters in the book that we will use only a small subsection of the book, but there's a ton of information in here, and right now we just want a basic introduction. So in chapter 3, there's only a few, really only a few sections you do need to look at. Obviously, in the introduction, that's pretty much typical. You probably should look at least the table in so read into 3.2. And then in 3.21, kind of look at the table that shows the different standards. It's just a long list of them. So no reason to memorize those or anything like that. The thing to remember is that Ethernet is 802.3. IEEE 802.3, as we talked about before. The link layer protocols and physical layer protocols are typically standardized through the IEEE. We'll come back to this chapter, by the way, because the 802 standards also include Wi-Fi, but we'll do that later. You definitely need to look at 322, the Ethernet frame format. That's the main thing we're going to talk about, and the main thing we will use in our labs and kind of going forward. We'll skip the next sections in 3.2. In 3.3, just look at the 3.3.3 link layer flow control, and it just sort of get an idea of what's going on. 3.4, read only the introductory part. Stop when you hit the spanning tree protocol, and even the 3.4 introduction is probably a bit more detailed than we need. But I'll kind of summarize that in the remainder of this video. So as you can see, you're really touching only a few sections. So keep that in mind and then focus on those sections. There's a ton of other stuff in here. We'll come back later to pick up some of the information about wireless, which is 802.11, but we're not going to do that now. Okay. So those are the sections in the book that match kind of with the content roughly that I want to talk about for this topic. Right. So a quick reminder: the Ethernet is. Oops. There we go. So Ethernet. I'm not going to draw all of them, but remember we have the physical layer. And then right above the physical layer is the link layer, just below the network layer. Ethernet defines both a physical and link layer procedures, so we will focus on the logic, meaning the link layer. The physical layer would be like electrically, how do you actually send a frame of information, right? And so we need to start with a little bit of history because Ethernet has evolved quite a bit over the years, and the book points some of that out. Get myself organized a little bit here. So originally, Ethernet, which won out, by the way, over a number of competing technologies at the time. We're talking about the 1980s or so. So Ethernet was really designed so that I would, in an office environment, I would literally run one long wire, basically a coaxial cable, and then all my workstations would tap into this cable. So this Ethernet was designed to be a shared medium, and somewhere here might be a router that actually connected off to the internet once that's what we're using Ethernet for. So Ethernet had to be a shared medium, which is why we used we already stumbled across the term MAC at some point. Ethernet needs media access control. And that's where MAC, media access control, comes from. The idea was that obviously if you have a single wire and a bunch of stations attached to it, really only one station can transmit at a time. How do you ensure that? And what Ethernet did was, first of all, obviously do the obvious. Each station listens and makes sure that there's no traffic on the wire. Right, so if there's a transmission going past, obviously you don't just transmit it on top of that. Problem is that even if you do that, it is theoretically possible and under heavy load, actually relatively likely, that two stations that are on different parts of the wire here, this station sees no traffic, starts transmitting at pretty much the same time this station starts transmitting, and on the wire that creates something called a collision. Which will garble both transmissions, and neither of the two transmission frames of data go through, which has to be repaired. And so, the original Ethernet protocol had a way to detect a collision, and basically the stations sort of randomly waited a period of time and then transmitted again, and that generally on the second try should work. If it's really loaded, the collisions might keep happening a bit more often. Right. So that's where Ethernet started. Most Ethernet networks today are not run that way. They've evolved since then, and use switches as opposed to just a single passive wire. Right. And so a modern Ethernet is let's see what we got here. So modern Ethernet has an Ethernet switch, and the various stations now all have their own wire coming from that switch. And that gives me some options, because now the control over the different wires is just a matter of the switch and the station negotiating. You can still get something that looks like a collision. Let's say that these. I'll grab a different color here. Let's say both of these stations. And typically, all of these are the same speed. Let's say both of these stations are trying to send a frame, an Ethernet frame, to this station here. Obviously, because they're all running at the same speed, that can't work. So the switch generally will store the frame and send them one after the other, which is very different from the situation in old Ethernet, where basically both frames would have been lost and would have had to been retransmitted. It's possible to overload the switch, and at that point it will discard frames. And then the higher level protocols further up in the protocol stack will take care of that. All right, so that's the physical architecture. Right, so today we'll have today obviously we'll not just use a single switch. It is it's fairly typical for us to build a network where, like at OU, there's probably a main switch in a building. There may be different switches for different areas, like each lab would have a switch. So it's perfectly possible to run a whole cascade of these things. obviously you try to minimize how much of that you do, but it's perfectly possible. Right, so you can interconnect switches. You have to be a little bit careful, and this goes beyond the scope of our class. You have to be a little careful because you can create loops, and in which case if the transmission will go around forever and ever and ever and break the network. So you have to be super careful. There's some sections in the book that we're skipping that talk about how you prevent that. So as long as you're reasonably careful not to do that, you can sort of cascade switches, string them one after the other, and extend your network that way. And because some of these links can be fiber optic cables for long distances, it makes it pretty easy to sort of extend Ethernet out if that's what you want to do. Right. So the final point I want to make in this video is that, and this is one of the sections that you definitely have to read in the book. Ethernet packets, the unit of data sent in Ethernet is called a frame. You'll see in a minute why that is. And I'm going to really simplify what's going on here. So a frame is essentially a packet, but with some particular properties. So even now, the IEEE is starting to use frame and packet somewhat interchangeably. You shouldn't. Ethernet really is referred as a frame, and should be. And IP packets are packets. So, and that also, keeps nomenclature clean a little bit. But what happens in the key components of an Ethernet frame, and we will at some point in the lab pull these things up in Wireshark, and you'll be able to see exactly, see examples of it and see exactly how they're built. But essentially, there is the frame has to, because of its origins, there's no control. It's just a wire connecting either multiple stations in the old Ethernet, or a wire that connects a switch to a computer. So when you start a transmission, you pretty much have to sort of wake up the other side and synchronize with it. So and I'm not going to go into the details. So there's a preamble, which is basically a set of bits that serve no purpose. They carry no data. The only purpose of these bits is to kind of wake up the receiver and let it synchronize, so it knows the right clock, the right speed at which the bits are being sent. So the preamble basically synchronizes the sender and receiver, and each station has both a sender and receiver, and in the sort of the switch architecture where you have a single wire between a station and the switch, you can transmit in both directions at the same time. It's called full duplex. So there's a separate sender, a separate receiver on each wire, on each side. So the preamble kind of wakes everything up. Then there is what for us is the most important part. There's a destination address. This is not an IP address. This is an Ethernet MAC address. The destination address is followed by a source address, so we know where it came from. Then the bit following this is kind of a weird field because it changed over time. So this is either a type or a length field. And almost everything you see today, it is a type field. It tells you what payload is in here. Now, obviously, let's use red. The purpose hold on a second there. So I'm going to use this. There's a couple more fields that serve sort of special purposes. If we have time, we might get to that. There's some add-ons like priority and those kinds of things I can insert into the frame. They would be here. Then the frame carries its actual payload, right? And let's say, so this could be an IP packet. It doesn't have to be. It could be something else. So generally, we refer to this as the payload. And then this is why Ethernet is called the frame. There is a field at the very end of the frame, which is something called a cyclical redundancy check. It's basically an error check. So when the transmitter, when the receiver notices that the transmission has ended, it will look at these bits here and it basically do its own calculation over everything else and compare what it got to this field. And if there was a transmission error somewhere along the way, it'll discard the frame, and a higher level protocol will take care of retransmitting. But the fact that there is the fact that the transmission doesn't end with a payload, it ends with another control field, is why people talk about a frame rather than a packet, right? Because it's framed by a control at the beginning and a control at the end. All right. So that's the basic layout of the frame. There's one final note before I wrap this up. The addresses are 48-bit addresses. It's kind of a weird number. It's a choice by the IEEE at the time that was an appropriate number. So these are 48-bit addresses, destination source address, and so that makes it 6 bytes. They are written generally in hexadecimal, so they're written as a hexadecimal string of numbers. Again, we'll get an opportunity to see that in the lab at some point. All right, that was kind of a quick review of the Ethernet topic and the sections of the book that go with it. I hope you found this useful, and I'll see you in the next video.